Hi everyone, today we're going to talk about the formation and evolution of high mass stars. So hopefully you tuned into the presentation of the formation and evolution of low mass stars. And part of this is relatively similar in that the stages for formation and evolution of low mass stars match those for high mass stars, with one exception. With high mass stars, everything happens much faster. In fact, it might take 100 million years for a low mass star to form out of a giant molecular cloud, but for a high mass star under greater gravity, that can happen in just a few million years or less. In fact, as we're going to discover, the high mass stars in a giant molecular cloud will often form, go through their stages of evolution, and explode before the low mass stars even finish forming. So when we talk about high mass stars in this presentation, we're mainly talking about stars that are going to end their lives as supernovae. That is, stars that begin with their lives with masses of more than about 8 times the mass of the Sun. Now, the exact cutoff on that really depends on how fast that star is going to rotate, how much in the way of metals it has in its atmosphere, that sort of thing, and it's actually rather complicated. But for our purposes, we're going to say that this cutoff is basically stars that are greater than 8 solar masses are going to explode. Those with less than 8 solar masses will not. What does that mean? Well, if you remember the formula about how luminosity of a star goes as mass to the negative 3.5 power, that means that the luminosity of the star goes as mass to the positive 3.5 power, which means that its lifetime goes as its mass to the negative 2.5 power. What that means is that an 8 solar mass star is going to pretty much go through the main sequence within about 50-something million years, and then only a few more million years as a red supergiant before it ends up exploding. So after about 60 million years, even an 8 solar mass star, the one at the low end of this, is going to explode as a supernova. And the higher the mass, the less time this is going to take. Here is a nice picture of a high mass star. This is a picture of the Bubble Nebula. It's a kind of nice shocked area of ionized gas formed by this 40 solar mass star around here, a nice O star, as we say, like the OBAFGKM scale, and it's ionizing all the region around it. That's called a Stromgren sphere. It's just the sphere emanating outward of ionized gas, and this particular star is an example of a star that will eventually explode. Here's a nice Hubble Space Telescope image of that same star, kind of zoomed in and with a nice different color palette. So showing some nice detail, very beautiful picture here. Now, the situation with low mass stars, recall from the main sequence, is that they end up becoming red giants, and then they end up coming back, and then they become asymptotic giants, etc. But in the case of high mass stars, instead of ending at the asymptotic giant branch with helium shell burning, high mass stars are actually going to continue igniting different higher elements in their cores, and then end up having shells around those that end up eventually igniting in nuclear fusion with even higher order elements in their cores igniting nuclear fusion, etc. There's going to be a kind of a nice onion diagram that we're going to get to on that relatively soon. And I should mention that each time this happens, the star loses more mass due to its expansion phase and high stellar winds. So in the case of your nice HR diagram, a 9 solar mass star is going to kind of evolve off. It's going to become a red supergiant, and then kind of come back and become a blue supergiant, and then end up becoming a red supergiant again and exploding. In the case of a 25 solar mass star, remember, things proceed more quickly the higher the mass is. It ends up becoming a red supergiant, and then back to a blue supergiant, and before it becomes a red supergiant again, it explodes. In the case of a 40 solar mass star, it ends up kind of blue supergiant real quickly, then a red supergiant, and then before it even becomes a blue supergiant again, it explodes. And an 85 solar mass star, that's going to explode right as it's leaving the blue supergiant stage. So, again, the higher the mass of the star, the more quickly everything happens. In the case of an 85 solar mass star, it's probably going to explode within a couple million years after it forms. So, again, these things end up exploding as supernovae. But before most of these things do that, they end up becoming what we call red supergiants. A red supergiant is a red giant, so to speak, except it's a high mass star. It's a much, much bigger object than just a red giant, and it has a much more tenuous atmosphere, and as a result, the spectral lines are much thinner, which is how scientists are able to distinguish between a nearby red giant compared with a faraway red supergiant. And some of these later evolve back toward kind of the blue range and become what we call blue supergiants, though, as we just saw, not all of them. Examples of red supergiants: Betelgeuse, one of the more famous stars out there in Orion. In fact, there's been a lot of news lately about Betelgeuse and its sudden dimming that was surprising to a lot of people. Antares, the bright star kind of in the northern part of the constellation Scorpius. That's a nice red supergiant. VY Canis Majoris, we've discussed that before. That's a red hypergiant, which again is a red supergiant with an absolute magnitude of less than -7 and has an extended envelope that's kind of getting streamed out into space. Now, a nice little activity is actually to find some of your own red supergiants by going to Google Earth and stuff like that. So yeah, as I mentioned, hypergiants are these red supergiants that actually have absolute magnitudes brighter than -7 and are rapidly losing mass. But yeah, it's a good activity is just kind of get out your laptops and find some other examples of red supergiants. And when I've done this in class before, an example a lot of people come up with is one of these nice stars that is losing a lot due to stellar winds, V838 Monocerotis. It was discovered to be a fairly strong variable star, and it was observed in 2002. And originally we thought it was undergoing a nova stage, where a white dwarf has a lot of material falling onto it that's able to start fusing again due to those enormous pressures and densities there. But eventually we realized that it's not the case at all. The star V838 Monocerotis is actually a 65 solar mass red supergiant. It's very much around the end stages of its life. It really is about to explode as a supernova, and it actually had a sudden, very active outburst as one of these, maybe even a pre-supernova event, where it suddenly got really, really bright. And when that happened, and that brightness ended up this sudden increase in brightness is kind of a burst of light that ended up going outward in all directions. This is a picture taken from the Hubble Space Telescope of V838 Monocerotis, and this burst of light ended up going outward in all directions, and it ended up interacting with a lot of this dust that had been cast off in the shells of the previous stages of the star's evolution. And as time goes on, well, the light travels out at, well, the speed of light. It ends up hitting other shells of gas. You can't see those shells of gas here because they're too dim right here. They haven't had an outburst of light. The outburst of light hasn't reached them yet, but we know that they're there because as the light ended up traveling outward, it ended up hitting those shells of gas, and we were able to see larger areas lit up because of this outburst that this central star had. And then time goes out even farther, you're able to see even more shells. Again, these shells were already cast off by the star long ago, like hundreds of years ago, but as the light travels outward, it's able to light up these different areas, but as it goes out, these areas that it lights up are more tenuous. See, for example, around here, you're actually able to see through this shell right here. And then finally, even later, the Hubble Space Telescope ended up taking a final picture of this thing, showing more of this kind of in outer regions, mainly behind the actual star, as the light travel time ended up being greater because the light has to go backward, and then it ends up coming toward us after it scatters off of that dust. By the way, we call this effect the light echo. Here is an artist's image of a dust torus around a dying supergiant star. So yeah, it's casting off outer layers during some of its final stages. It's not casting them off to eventually reveal a white dwarf. Remember, these are large stars, so eventually these things are going to explode. But nonetheless, they are casting off outer layers. Notice that there's this torus shape because of conservation of angular momentum, also probably having to do with some alignment with the star's magnetic field. Now, in terms of evolution and fusing of heavy elements, remember, a main sequence star, by definition, is fusing hydrogen into helium in its core. core. That's what we mean by main sequence star. The method it uses to do this, well, that really depends. Again, remember, for stars like our Sun, it's mainly the proton-proton chain, but once you get up to about 1.3 times the mass of our Sun or so, the CNO process, carbon, nitrogen, oxygen process, starts to kind of take over more of the percentage of that, where carbon ends up being used as a catalyst in the eventual fusing of 4 hydrogen atoms into a helium, or 4 protons into a helium nucleus by the time that set of steps is done. If you're unfamiliar with that set, then go back to the previous video where I went through the formation and evolution of low mass stars and explained that in some detail. So, in the case of high mass stars, though, in fact, for that matter, I'll mention that this happens in any star that's more than about 4 times the mass of our Sun. Eventually, temperatures in the core reach about 600 million kelvins, and that's hot enough not just to fuse carbon-12 plus some of those helium-4 nuclei, which even our Sun's eventually going to do that to end up creating some oxygen-16 nuclei. But once you hit 600 million kelvins, carbon nuclei and carbon nuclei are able to fuse together, and through a variety of interactions. You can get neon-20 this way, you can get sodium-23 this way, you can get magnesium-23 this way, and it ends up leading to some of those elements on the third row of the periodic table. So when this happens, you end up getting some protons, neutrons, and alpha particles that end up getting liberated like this. And again, you can produce neutrons by a number of these types of interactions. It even occurs in Sun-like stars. In fact, that's why you end up getting slow neutron capture nucleosynthesis during the asymptotic giant branch, because a lot of these lower level nuclear reactions are also producing neutrons in some cases. But these neutrons, which are just floating around in there, well, by slow neutron capture, the same process that actually forms about half of the isotopes on the periodic table heavier than iron-56, these are able to form things like aluminum, silicon, phosphorus, stuff like that, just during the normal evolutionary stages of a massive star, and even an intermediate mass star. I'm thinking of an intermediate mass star as a star between about 4 and 8 solar masses, where you'll get this carbon-carbon fusion, but they won't end up exploding in the end. Now, eventually, these nuclei that are created end up participating in further nuclear fusion, but as that's happening, the temperature eventually reaches 1 billion kelvins. That's actually hot enough for something called photodisintegration, where at 1 billion kelvins, this is a very, very high temperature. These photons are very high energy gamma rays, and this is a high enough energy gamma ray that a photon of this kinetic energy is able to smash into one of these nuclei that's being created and bust it apart. It's kind of like it's undoing some of this nuclear fusion. So, for example, this neon-20 might end up getting busted apart into oxygen-16 plus an alpha particle, but that's not completely undoing things. These extra alpha particles that are being created, remember, it had been a carbon core before, but now we have some of these alpha particles back. These alpha particles can start smacking into some of these other neon nuclei to create things like magnesium-24, and further on up the chain. Now, eventually, there ends up being a phase of this neon photodisintegration, and you end up creating this magnesium-24. This oxygen-16 that's been left over from the photodisintegration of the neon-20, well, some of these oxygen atoms start to smash together. Again, we're talking about 1 billion kelvins here. That's a lot of energy. That's able to create silicon-28 plus helium-4, an alpha particle that is. Or it can just directly create sulfur-32. That's how you create a lot of the sulfur-32 that's out there. You know, that yellowish element once you get 8 sulfur atoms bound together. So, yeah, if you don't have 8 or more, it's not going to be yellow. It's going to be some other color. But anyway, at this time when you get oxygen fusion, here we're talking about 2 billion kelvins. And here we're getting close to something quite remarkable, because once you start getting this, here eventually you're going to start fusing silicon. And once silicon starts to fuse, this is going to very quickly start to accumulate iron in the core. This happens at about 3 billion kelvins. So silicon ends up fusing, and you end up getting iron in the core, and this is really kind of a diagram of what you're dealing with in one of these types of stars. You get an iron-nickel core, and then outside of that, you have a shell that's fusing silicon. Outside of that, you have a shell that's fusing oxygen. Outside of that, neon. Remember, oxygen is inside of neon because the neon's being photodisintegrated. And then outside of that, you have a shell of carbon, and outside of that, you have a shell of helium. Outside of that, you have a shell of hydrogen. So eventually, though, we end up reaching this core of iron. And iron is actually very, very special. It's something that I've alluded to previously in the course, but it's something that we want to come back to now because this is actually very, very important here. Now, before we really get into that in detail, just looking at that picture in that diagram, you might think, how can we go directly from silicon to iron in the core? Well, this actually takes place in a number of steps. So it's not just, oh, silicon plus silicon ends up yielding iron plus stuff. So we actually have things like silicon plus helium gives you sulfur-32, and sulfur-32 plus helium gives you argon-36. And then eventually, by continuously adding on alpha particles and some neutrons and also some radioactive decay, you eventually end up getting iron-56. For example, one of the things you end up getting up to is things like nickel-60 or cobalt-60, and some of that's going to end up decaying into your iron-56. But there are also other nuclear reactions there, as well as just some neutron captures. But in terms of timescales, so a 20 solar mass star is going to spend 6 million years on the main sequence. Again, that's a calculation you can do. Remember, lifetime is proportional to the mass to the minus 2.5 power. So that means it turns out it's also going to be in the helium burning stage. There's another equation for that. That's going to be for about another million years. It's going to be fusing helium. After that, that carbon-12 plus carbon-12 stage, that lasts for about 300 years. And then after that, the oxygen burning stage only lasts for 200 days, and the silicon burning stage lasts for only 2 days. Why is it so much less time as we keep going up, you might wonder? Well, it has to do with the fact that, one, you're dealing with a lot higher temperatures, so the reactions proceed faster, and two, you don't have as much oxygen as you had carbon, and you don't have as much carbon as you had helium. So that's why those things combined end up making these timescales much less as you go farther up the stage. In fact, there's also another reason that we're going to get to soon when we show this chart that I have that will really end up bringing this up, because of the fact that also as you go higher and higher into the periodic table with these fusion reactions, you don't get as much energy out of the reaction. And because you're not getting as much energy out of the reaction, you need to have more reactions. And with the temperature being higher, that is going to be the case. So it happens much faster as you get higher up into the periodic table with these fusion reactions. Now, again, this happens even more quickly for more massive stars. For example, back in the late 1830s, in fact, and then into the early 1840s, there was the star Eta Carina. I've mentioned it before. It may have had an initial mass of about 150 times the mass of our sun, and it had a very significant outburst that temporarily made it the second brightest star in the evening sky, after the star Sirius. Now, just to put this in perspective, the star Sirius is something like 8.6 light years away. The main reason why it's the brightest star in the evening sky is that it's one of the closest stars to our sun, at like 8-point-something light years. Well, Eta Carina is about 7,500 light years away. So almost 8,000 light years away, and nonetheless it was the second brightest star in the night sky for a time after this outburst that it had, which might have been a pre-supernova event. There has been some speculation that that was due to the beginning of it starting to fuse carbon with carbon, and the reactions that ended up proceeding in instabilities from that as well. It's really hard to say, though. It's very difficult to successfully model what actually is going to be the effects on these types of stars when that happens, especially since mainly it turns out because of the fact that we do not have a good understanding of the opacities of the different atomic species and how those occur in these cores. Opacity is the degree to which light is absorbed by a particular atomic species. So that's something to keep in mind as well. So it's difficult to successfully model this with computers at this point, even in 2020. But in any case, after silicon burning finishes, the core of this star is going to be rich in iron group elements. By iron group elements, I'm mainly talking about iron and nickel here, and also some cobalt, although a lot of that's going to be radioactive at this point. But once you start fusing silicon, the core is past the point of no return. In fact, there is a, if you were to click on this, it would end up taking you to a YouTube video of the song from The Phantom of the Opera. Now, why is iron 56 so significant? I've mentioned it before in earlier discussions, and iron 56 is significant because it has the least mass per nucleon. Remember, a nucleon, that's just a proton or a neutron. So when we talk about, let's say, iron 56, that number 56, that's the nucleon number. So if you take the actual mass of iron, which is like 55.846 AMUs, something like that, and divide by the number of nucleons it has, which is 56, you actually get the smallest number that you get for just about any nucleus. I mean, even in the case of uranium-238, uranium-238, for example, well, take the actual mass of uranium-238 is like 238.0 something AMUs, but you divide that by 238, well, that number is greater than 1, but you divide 55.846 by 56, that number is less than 1. So yeah, iron 56 actually does have the least mass per nucleon, or at least roughly the least mass per nucleon. I say roughly because there are a number of other atomic species that are fairly close to iron on the periodic table that also have similar mass per nucleons. Well, why is that? That's because the binding energy is so large in size. And remember, binding energy is negative, so that results in a decreased mass. But what that means is that if you're to make a plot of binding energy per nucleon versus mass number, that plot's going to end up being something like this. By the way, notice these are negative numbers going down here. I think that's especially important because of the fact that binding energy is negative. So what's going to happen is, as you go closer, if you engage in nuclear reactions, if you produce nuclear reactions that result in the products of the reactions being closer to this bottoming out area, the result is that you're going to gain energy out of those nuclear reactions. So in the case, like right here, we're talking about just hydrogen. Well, proton-proton chain, you're going to end up getting helium-4. Whoa, that's a very big difference in energy. You end up getting a lot of energy out of fusing hydrogen into helium, no matter how you do it, whether it's by the CNO process or by the proton-proton chain. What really dictates how much energy you get out of that is what's the difference between the energy right here, the product, and the energy right here, the reactants. Well, here we're talking about a very large difference in energy. And I think, let's see, over here, this little dip right here, this is carbon-12. Well, notice there's not all that much of a difference between helium-4 and carbon-12. You can also see why it's so difficult to get from helium-4 to carbon-12 with that triple alpha process, because everything in between helium-4 and carbon-12 has a higher binding energy per nucleon, which means that you would end up needing to consume energy in order to get something like that in between. So, in any case, though, that kind of goes in with the fact that, yeah, once you get higher up the periodic table, you're not getting as much energy out of this reaction. How much energy are you getting out? Well, it's the energy difference between this point and this point. But since you're not getting as much energy out, you need to have more reactions in order to produce the same amount of energy, which means that you're going to end up using up this helium-4 more quickly once it goes into carbon-12. Well, carbon-12 to oxygen-16, well, that's an even smaller energy difference. Carbon-12 and a neon-20, because remember, carbon-12 plus carbon-12 ends up giving you neon-20 plus an alpha particle. Again, that's a smaller energy difference. So as you keep going on here, you're talking about smaller and smaller energy differences from one stage to the next, so the reactions proceed more quickly. But iron 56, right around here, this is where everything bottoms out. You cannot actually expect to obtain energy by fusing iron 56 in with something else. Instead, that you end up having to sap up energy. You end up having to use energy in order to have iron 56 fuse with other nuclei. Now, you can get these other nuclei, but in order to get these other nuclei, we're talking about other types of nuclear reactions, which we're going to get to. In fact, we've already discussed one of those. That's the slow neutron capture process, but that is not what's actually going to go on when the star explodes. So who cares about this iron 56? After all, sorry, iron 56 would be around here. So after all, iron 56, I mean, it's like, okay, fine, it ends up accumulating in the star's core. Why does that make the star unstable? So again, if you're to the left of this bottoming out, you get nuclear energy by fusion. If you're to the right of this, you get it by nuclear fission, that is splitting things apart, like atomic bombs, that sort of thing. But in any case, why do we care about building up this mass? So again, you end up, it's like, okay, who cares if you end up having a net loss in energy? Well, there's a problem. Something that we've kind of very briefly referenced at other points in the course is that there is something called the Chandrasekhar limit. The Chandrasekhar limit is the maximum mass that you can have for a cold, dead object. And by cold, I don't mean cold in temperature. I mean something that is no longer participating in nuclear fusion. So a cold, dead object, that's a white dwarf star. Well, a white dwarf star can't be any more than about 1.38 times the mass of our sun when you talk about the typical types of elements that would tend to exist in these things. Like we're talking about carbon, oxygen, white dwarfs, or oxygen, neon, white dwarfs. So 1.38 times the mass of our sun. You can't be more than that. So what that means is that the core of a star cannot support itself against the inward pull of gravity if it's 1.38 solar masses or more. So in the case of our sun, well, we're not going to have to worry about that. The core of our sun, once everything ends up getting said and done with, it's only going to be about half the mass of our sun is right now. The white dwarf Sirius B, that little white dwarf star orbiting around the main star Sirius that we're all familiar with, that has a mass of about 1 time the mass of our sun. So there's not a problem there. The outward push is able to support itself against the pull of gravity. Now, what is that outward push? That's something called electron degeneracy pressure. Electrons are special particles. They're a general group of particles called fermions. There are lots of different types of fermions. Protons are also fermions. But a fermion is any particle that has what we call half-integer spin. Don't worry about what that is, though you might remember something like that from chemistry class, how electrons have this either plus or minus 1/2 spin, and you can't put 2 electrons in exactly the same quantum state. That's the Pauli exclusion principle. So when you were filling out these electron shell diagrams in your chemistry classes, you ended up, like for say oxygen, you had your spin up, spin down in the lower energy level, and then in the next energy level, it's like, okay, first you start off with 4 slots, but each slot can have 2 configurations. So you fill out first, you have spin up, spin up, spin up, spin up, and then the next 2 are spin down, spin down. They can't be spin up because the 4 spots are already filled for spin up, so you have to have spin down. So that all happens because of the Pauli exclusion principle. Well, it's this Pauli exclusion principle that produces this electron degeneracy pressure. The gravity really wants to pull this cold, dead core inward to cause it to collapse even further, but the electron degeneracy pressure that exists due to this Pauli exclusion principle is able to support that for quite a long time. In fact, it can support that all the way up to 1.38 times the mass of our sun. But here's the thing. Once the star dies, that's a problem. Why wasn't it a problem before the star died? Like, say, for a 10 solar mass star. A 10 solar mass star is eventually going to end up getting a core that is more massive than 1.38 times the mass of our sun. Why do we care about that? Well, that's able to support itself against the inward pull of gravity because it has something in addition to electron degeneracy pressure supporting it. It has nuclear reactions. These nuclear reactions are very energetic. They're able to help support the core against collapse. But once those nuclear reactions turn off, the only thing preventing that stellar core from collapsing is the Pauli exclusion principle. But that only works up to the Chandrasekhar limit, that 1.38 solar masses. So the result is that the core ends up collapsing. As this occurs, you get a big slew of nuclear reactions from these collapsing shells that are falling on top of that, basically kind of bouncing back. You get this big slew of nuclear reactions, and this produces a huge burst of neutrinos. These neutrinos are actually able to a lot of them are able to travel outward from that core, but it ends up being so dense that even the neutrinos end up getting kind of blocked for a bit of time, and that ends up producing kind of a shock, which ends up really, it turns out, helping to cause the star to explode. But during the initial explosion, 99% of the energy of the supernova is actually produced by neutrinos. Because of these extremely rapid nuclear reactions. What kind of rapid nuclear reactions? Well, mainly something called the rapid neutron process, the R process nucleosynthesis. We're going to get to that relatively soon. But in any case, these overall details are what we call a core collapse supernova. The core of the star has collapsed, causing a big explosion. The star ends up exploding because of the collapse of layers outside of it. They end up bouncing back, and again, you get lots of these nuclear reactions. But this is what we call a core collapse supernova. There are different types of supernova based on the spectra that are produced when these things explode, and long ago scientists distinguished between type 1 supernovae and type 2 supernovae. Type 1 supernovae are the distinguishing features between whether they have hydrogen in their spectra, that's the case with type 2 supernovae, or whether they do not have noticeable hydrogen lines in their spectra. Those are what we call type 1 supernovae. Now, all type 2 supernovae are some sort of core event supernova in which something has happened in the star's core to cause the star to explode. There's a special type called type 2p. These are the pair instability supernovae that I've referenced before. In that case, it's not a core collapse, but it's still a special event in the core. Type 1 supernovae, a lot of type 1 supernovae are also core collapse supernovae in which the star has simply already cast off its outer hydrogen layer. But there's also a special type of type 1 supernova, type 1a supernova, that we're going to discuss in the next PowerPoint. That's a very different type of event. But in any case, we're talking about core collapse supernovae today, and these are situations where you end up getting mainly an iron-nickel core, and that ends up collapsing once nuclear fusion turns off. So, in terms of timescales, again, we mentioned that core hydrogen burning, core helium burning, core carbon burning, that 300 years. Core oxygen burning takes 200 days. Core silicon burning, that's 2 days. So once you get enough silicon in that core to start igniting that silicon in nuclear fusion and eventually building your way up to iron 56, once the silicon starts burning, that's 2 days before the supernova is going to occur in a star initially 20 solar masses. Once you end up getting that iron core ends up eventually collapsing. That takes about 1 second or so. But it does take some hours for the actual detonation to make its way to the surface, because you have all of this surrounding star collapsing onto the core, and the energy itself ends up getting stuck from all that. You end up getting all these nuclear reactions, this R process nucleosynthesis and stuff like that. But the neutrinos actually end up making it out first. In fact, the last supernova that was visible to the unaided eye occurred in 1987. That was in the Large Magellanic Cloud, a galaxy orbiting the Milky Way. The neutrinos from that supernova arrived at Earth's neutrino detectors several hours before we actually saw the star visibly explode. In terms of the appearance, well, what's it going to look like? It's just going to look like a very, very bright star. The overall brightness of the star, when you take the energy at all wavelengths, it's going to rival the combined brightness of all of the other stars in the galaxy. So it's something that you'll be able to see. If you're looking at the galaxy in a telescope, it's really going to stand out compared with the rest of the galaxy. It's just going to look like an extremely bright star. So at first, most of that luminosity is contributed by thermonuclear reactions, but as you get brighter and brighter, a whole lot of that is actually being produced by the glow of the decay of radioactive elements. We're talking about especially things like nickel-60, cobalt-60, stuff like that. So here's an example. The cigar galaxy, M82, just a normal picture of it on the left, but it actually had a nice supernova event back in 2014, and that was this star right here. This event was bright enough that if you had good binoculars, you could have actually seen a very faint star there where there previously was no star. So it was kind of a relatively recent supernova, but you needed good binoculars or a telescope to be able to see that. These things have cosmological significance. For example, astronomers like to study deep galaxy surveys and then study the same field again to see whether there are any supernova explosions. So here was one that occurred in this very, very distant galaxy, billions of light years away, that we saw back in 2002. In fact, the witnessing of these help us to determine the history of the universe's expansion rate. Now, other supernova events. In the year 1054, a very important one occurred. This was when a star suddenly appeared very brightly all over the world. It was recorded by the Mayans. It was recorded by the Chinese. Strangely enough, it was not recorded by the Europeans, but that was also the year of the Great Schism, so I guess they had their hands full. But this thing became bright enough to be visible in full daylight for a couple of weeks. And it eventually diminished from view at night about a year later, but it was bright, again, it was bright enough that you could see it in full daylight for a couple of weeks. And there was actually another one in the year 1006 that was bright enough that people were able to use its light to read at night. There was also another one in the early 12th century, and that was bright enough to be seen during daytime as well. At the core of the supernova remnant is something called a pulsar. This is the remnant of that explosion. Most nebulae, as you know, you're talking about collapsing objects, star-forming regions, that sort of thing. But a supernova remnant, this is the Crab Nebula, the first object in Charles Messier's catalog of fuzzy things that aren't comets. It's a supernova remnant. Ironically, the first object in that catalog is actually the only supernova remnant in the catalog. But anyway, the very center of this is a pulsar. Remember how we talked about white dwarfs having a maximum mass of 1.38 solar masses? Beyond that, that Chandrasekhar limit, the electron degeneracy pressure, cannot support them against further collapse due to gravity. Well, a neutron star is what a pulsar is. A pulsar is a spinning neutron star. That core, what would have otherwise become a white dwarf if it was less than the Chandrasekhar limit, that has collapsed into an object so dense that it's composed of mainly neutrons. It has a whole lot of neutrons in there. There are also free-floating protons around, and also things like iron-56 nuclei, stuff like that. But you have a whole lot of neutrons, so we call it a neutron star. And it's neutron degeneracy pressure that's able to support this thing against further gravitational collapse. How big? We're talking about something that's more than the mass of our sun in a space that's only about maybe 12 miles in radius. So we're talking about an extremely dense object here. It's spinning very rapidly, in this case about 20 times per second. That ends up, here we're talking about something that already started off with a magnetic field. You end up getting a very strong magnetic field around this situation, around this neutron star, and that ends up kind of tying in this spinning gas around it. This is a picture that was taken with the Chandra X-ray Observatory. So this is very hot gas heated in X-rays. The one that I mentioned before, supernova 1987A in the Large Magellanic Cloud, kind of near the edge of the Tarantula Nebula, that was 163,000 light years away. But even so, it was bright enough that if you were looking there, you could see it. It had an apparent magnitude, I think, of about +2. So kind of similar to what Mars is when Mars is kind of dim, but still brighter than the great majority of the stars that you can actually see. So the star that exploded was actually a 25 solar mass blue supergiant. It was a star that had already been cataloged. And this was something that surprised astronomers because in the 1980s, it was believed that only red supergiants explode. That was just a result of the theoretical calculations that we had leading up to that point. But this was a blue supergiant that exploded. In fact, we now realize that a whole lot of the supernovae that we witness in other galaxies are actually due to the explosions of blue supergiant stars, interestingly enough. But in any case, we believe that when the star Betelgeuse explodes, it'll actually explode as a red supergiant, just like it is right now. It's believed that Betelgeuse will explode sometime between about 20,000 and 100,000 years from now. Here is that remnant. It's actually this thing very close to the center. The rest of this is actually the nebulosity from this Tarantula Nebula. Remember, I mentioned that the star was kind of around the edge of the Tarantula Nebula? Well, this is a lot of the nebulosity from that. But here's the remnant. If you zoom into that, you get these nice little concentric rings. Now, why are these ellipses? Why are these not circles? They're ellipses because you have this kind of occasionally the central area here ends up having kind of an outburst of luminosity, and that ends up reflecting off of these rings. And thing is, it actually is a ring. It's a circular ring, but we're seeing it at an angle. And since we're seeing it in an angle, that means part of the ring is closer to us than the other part. So what happens when the central region here, the remnant area, ends up kind of having some shock that ends up making it brighter? Eventually that light, remember the light echo that I mentioned with V838 Monocerotis? It does the same thing over here. But the near part gets brighter sooner than the far part. But the time difference between those allows us to very precisely determine the actual diameter of this. Also, we can figure out the diameter of this in other ways from geometry as well. But in any case, the precise timing of that does allow you to determine the diameter of this ring, that time difference, because we know the speed of light, we know the angle of this because we know that it's really a circle, not an ellipse, as are these. And from that, you can actually get the diameter of this relatively precisely. Well, based on how large the thing looks in the telescope, this is a direct geometric determination of the distance to this, 163,000 light years. So we got this directly from geometry. Well, that's pretty good. We don't have to use the cosmic distance ladder, Cepheid variables, main sequence fitting, or anything like that. We can just get the diameter directly from geometry, or sorry, the distance directly from geometry. That's pretty cool, and that's also very important. Here it is again. Just to show you what this looks like when it is kind of lit up due to interactions involving whatever's at the center here. So far, we do not know exactly what's at the center here, whether it's a black hole that's interacting with material around it, or whether there's a neutron star there, or maybe even nothing at all. Not all of these core collapse supernovae necessarily leave behind a neutron star. That's one of the results from research over the past decade or so, that you don't necessarily leave behind a remnant. Whether a remnant is left behind often depends on other things. For example, the rotation rate of the object that ended up going in there, how much in the way of metals were in the star to begin with, at the beginning of its life, that sort of thing. So how important convective overshooting is during the star's lifetime. So it's actually kind of complicated in determining whether or not you're going to get a neutron star or just no remnant at all from, say, something like a 20 solar mass star. And there it is, zoomed in again. Just to compare, before that blue supergiant star, it's in this picture right here, but when it exploded, kaboom, it just lights up like the 4th of July. In terms of what's actually going on in the central region right now, if you were to view that ring at the right angle, again, we don't know what's there in the middle, if anything, but still there's a whole lot of gas here that's interacting with these various shock waves that were produced from the supernova event itself and thereafter, that were I should say, triggered by the supernova event itself. And when you get these shock waves interacting with reverse shock waves, you can end up getting the central area suddenly lighting up, and that can produce a big pulse of light that ends up hitting the outer regions, which we end up seeing very, very nicely as well. By the way, in terms of these hot fingers in here, this is actually kind of like a lava lamp. You still have some gravity here, and if you have an area here that is less dense than the material that is outside of that, well, that ends up creating a Rayleigh-Taylor instability, and you can get these kind of finger-like regions in the form of which is how a lava lamp works. So I'll show you a few other supernova remnants as well. This is something called the Veil Nebula. It's part of a larger supernova remnant called the Cygnus Loop in the constellation, surprise, surprise, Cygnus. It's actually something that you can see with good binoculars or a small telescope as well. It's a very nice supernova remnant. Here's a zoom into part of the Veil Nebula from the Hubble Space Telescope, and the colors in this case are not quite real. They used a different color palette to highlight the emission from different elements and different ionization species so that we can learn more about the object, but still the result is that it creates pretty space art. Here's another nice supernova remnant, and this is also a supernova remnant. You might think, oh, isn't this a planetary nebula? Nope, this is a supernova remnant, as it turns out. Now, I've mentioned that you end up getting a lot of heavy elements forming as a result of this. This is due to something called R-process nucleosynthesis. So we call it R-process because it's rapid neutron capture as opposed to the S-process, which is slow neutron capture. So something that occurs even, again, in asymptotic giant branch stars is you'll have, say, free protons roaming around, and sometimes these protons can interact with an electron antineutrino, and the result of that is the formation of a neutron plus a positron. Well, those neutrons end up participating in nuclear reactions very well because they end up getting they get stuck to atomic nuclei because of the fact that there isn't this repulsion due to positive and positive repelling each other, but you still have the attraction from the strong nuclear force once they get close enough. So this happens in asymptotic giant branch stars, the slow neutron capture process, but it also happens in the rapid neutron capture process in stars that are in the process of exploding. You get lots of these interactions with a lot of these protons. Also, a proton near something else can, quote, decay into a neutron plus a positron plus an electron neutrino in that case, but that's a reaction that can only happen when it's near something else. Well, guess what? During the collapse of a massive star, the environment is extremely dense, so that sort of reaction is actually happening all the time, and you get lots of neutrons by this process, and these neutrons are very rapidly absorbed in interacting with these other atomic nuclei that are getting produced. So you very quickly work your way up the periodic table. You end up getting beta decays, inverse beta decays, or various weak nuclear reaction processes that result in an increase in atomic number with the same atomic mass, that sort of thing. Because here's the thing. You start off with, say, let's just say iron-56. Well, what's a neutron going to do with iron-56? Well, that's going to end up giving you iron-57, another neutron, iron-58, stuff like that. Well, iron-57, iron-58, these are not stable. And you're going to end up potentially getting things like beta decays that end up, instead of getting, say, I don't know whether this reaction actually occurs, but just to illustrate the process, this iron-57 could end up becoming, in this case, the next element up after iron. So that iron-57, that would potentially beta decay to the next element, which in that case would be cobalt-57. Though I actually did just look it up. Iron-57 is stable. So you would end up getting iron-57, and then you get another neutron hitting that. That would be iron-58. Then you get another neutron hitting. Iron-58 is also stable. It's just not very common because it's very easily captures neutrons. After that, you get iron-59. That's unstable. Usually before that decays, you end up getting iron-60. Well, iron-60 is unstable. That ends up beta decaying to cobalt-60. Cobalt-60 is also unstable. That ends up beta decaying to nickel-60. You might remember this. I had already mentioned iron-60 and cobalt-60 before. That's what ends up making these supernovae, these type 2 supernovae in particular, really bright when they're at their peak brightness. It's the beta decay of cobalt-60. But anyway, nickel-60 is actually stable. But then you can start getting more process nucleosynthesis. So you get like nickel 61, nickel 62, etc. And once you get nickel 63, that ends up, if I remember correctly, being unstable, and that ends up beta decaying, etc. So you get the point. You end up very quickly getting up to high elements on the periodic table this way. This is one method behind which we get the very heavy elements like gold and platinum and iridium and uranium and stuff like that. In fact, it is believed that you can go all the way up to the element californium as a result of these supernova explosions. That's atomic number 98, but californium is pretty unstable and ends up alpha decaying pretty quickly, which is why we don't have californium naturally occurring on Earth. So the heaviest naturally occurring element on Earth is plutonium, which you can get from the decay of uranium ores interacting with things like cosmic rays and stuff like that. They found trace amounts of neptunium and plutonium and uranium ores. And also at the bottoms of the oceans we occasionally get small amounts of plutonium from these types of reactions, but very small amounts. Overall, though, we've lost most of the plutonium that we originally had because the longest lived isotope of plutonium, that is plutonium-244, does not live all that long. You also can get gold from these types of stellar explosions. In fact, every atom and nugget of gold in the universe was formed in the intense heat and energy of some type of stellar explosion. Now, there are multiple ways that this can happen, and I'm going to address that very soon. Results of some new research on this. Old studies suggested that all of this just came from our process nucleosynthesis, but there have been newer studies which have been making some news over the past few years about how it's believed that there could be a whole lot of this occurring due to the collisions of neutron stars. I should mention also again that a lot of the other heavy elements occur due to white dwarf supernovae, as well as stars that are, say, 1 to a few times the mass of our Sun in the asymptotic giant branch by S-process nucleosynthesis. Now, as I mentioned, there is recent research that seems to be calling into question the concept of most of the gold out there coming from core collapse supernovae. Analysis of old stars has found these things to be highly enriched in elements like barium and europium and actinides on the periodic table. Actinides, the most famous ones being thorium and uranium. And that seems like a problem because in fact, I'm just thinking of a graph that I don't want to really post it because it's more technical, but long story short, the ratio of barium to hydrogen or uranium to hydrogen, if you plot it versus the ratio of iron to hydrogen, and by the way, when you put brackets around this, it's what the brackets mean is you take the ratio of barium to hydrogen in the star and divide that by the ratio of barium to hydrogen in the sun. The brackets mean, hey, you're comparing this ratio with that same thing for our sun. Or, again, with europium to hydrogen and iron to hydrogen. So what we're saying is that in these stars that they've been studying, these old stars, they have found a significant enhancement of barium to hydrogen relative to iron to hydrogen when compared with our sun. Well, what does that mean? Well, that means that whatever nuclear process is occurring here is producing a lot more barium and europium and other things like thorium and uranium than you would expect just from looking at how much iron is in there. Because we think, okay, core collapse supernovae, you end up having a star that's produced a whole lot of iron, and you end up producing a lot of barium and europium and thorium and stuff like that from the nuclear explosion, that sort of thing. That was the previous idea. But now we're realizing that in these stars, there's been a significant nuclear process that has produced a lot of barium, europium, thorium, etc., without producing a whole lot of iron. Well, these core collapse supernovae, they're producing lots and lots and lots and lots of iron. So where's the, you would expect that, and maybe less of the barium and europium. In fact, according to those calculations, you'd think, okay, you're not going to be able to produce all that much barium, europium, thorium, gold, platinum, etc. from core collapse supernovae. So the idea is that that stuff is produced by the collision of neutron stars. So these neutron star mergers, they end up not producing much iron. So, I mean, yeah, they'll produce some, fine, because after all, these neutron stars ended up being leftover iron cores anyway, except a lot of those have become protons and neutrons due to the densities. But it does end up producing a lot of the other stuff on the periodic table. However, I want to bring in an additional note. So right now, that is, as of April 2020, these studies have mainly been of stars that either inhabit other galaxies, that is, not the Milky Way, or they're very old stars that are in the Milky Way. So the question is, well, maybe would this necessarily apply to young stars? In other words, things like our sun. Remember, our sun is a population 1 star. It is believed by many that most of the heavy elements in our solar system were produced by the explosion of another star that formed in the same giant molecular cloud as our sun. That also would have been a population 1 star. That is not an old star. That's a young star. In other words, would this necessarily be the case with stars that already start off with a lot of metals? So the question is, where did we get our gold? Well, long story short, we really do not know. In fact, I will mention an even more recent study. Another April 2020 study, I should say, seems to indicate that in a lot of core collapse supernovae, in particular stars with between something like 18 and I think like 30 times the mass of our sun, or actually I think it went up to about 50 times the mass of the sun in one of these studies, they ended up revealing that what could end up happening in this core is a conversion of the state of matter to something called a quark-gluon plasma, which otherwise it's something that existed up until about 1/1,000,000th of a second after the Big Bang, maybe 1/1,000,000th of a second, I forget, but it's a very tiny fraction of a second after the Big Bang. But this quark-gluon plasma is a very special state of matter, and these studies from recent supercomputers are indicating that, yeah, maybe this could end up happening in the cores of these stars that are exploding. And when that happens, it ends up igniting a different type of chain of reactions. You end up getting not so much iron, you'll still have some iron, but not as much iron, and more in the way of things like europium, thorium, barium, gold, and stuff like that. So if that's the case, then you don't necessarily need these neutron star mergers in order to produce our gold. So where do we get our gold? Well, we really don't know for sure, but either way, we're talking about some sort of stellar explosion. So there is a gold nugget at the end, and thank you for watching. If you have any questions, please let me know in the comments.